Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why silicon-based life forms might be possible. For as long as scientists have contemplated life beyond Earth, one element has persistently captured imaginations as a possible alternative to carbon, silicon. Science fiction has explored silicon-based aliens in countless stories, from rock-like creatures that metabolize minerals to crystalline beings that think at geological timescales. But these fictions rest on a foundation of genuine chemistry. Silicon sits directly below carbon in the periodic table, shares many of carbon's most important properties, and is far more abundant in Earth's crust than carbon. Yet despite this abundance and chemical similarity, silicon never became the basis for life on Earth. Understanding why silicon-based life might still be possible elsewhere requires examining both the remarkable parallels between silicon and carbon chemistry and the significant obstacles that would need to be overcome. Carbon's dominance in biochemistry stems from several key properties. Carbon atoms can form 4 strong covalent bonds with other atoms, allowing them to link together into chains, branches, and rings of almost unlimited complexity. A single carbon atom might bond to 4 other carbon atoms, creating a 3-dimensional network. Or carbon atoms might link into chains hundreds or thousands of atoms long, with various other elements, hydrogen, oxygen, nitrogen, phosphorus, sulfur, attached at different positions. This versatility allows carbon to form millions of different molecules, from simple methane with 1 carbon atom to DNA molecules containing billions of carbon atoms arranged in precise sequences that store genetic information. Silicon shares carbon's ability to form 4 covalent bonds. The electron configuration that gives carbon its bonding properties is mirrored in silicon, making silicon capable of forming similar structures: silicon chains, silicon rings, silicon networks. In fact, silicon chemistry forms the basis of an entire class of synthetic materials called silicones, which consist of chains of alternating silicon and oxygen atoms with organic groups attached. These materials, familiar as sealants, lubricants, and medical implants, demonstrate that silicon can indeed form large complex molecules. But silicones are human inventions, created in laboratories and factories. Nature has not produced silicon-based organisms, at least not on Earth, despite silicon being about 900 times more abundant in Earth's crust than carbon. The primary obstacle to silicon-based life under Earth-like conditions is silicon's relationship with oxygen. When carbon reacts with oxygen, when it burns, it forms carbon dioxide, a gas at normal Earth temperatures. This gas can be easily expelled from an organism and recycled back into the environment. Plants take in carbon dioxide and use it to build sugars through photosynthesis. Animals exhale carbon dioxide as a waste product of metabolism. Carbon dioxide dissolves readily in water, allowing it to be transported in blood and participate in various chemical reactions. The carbon cycle that sustains Earth's biosphere depends on carbon dioxide being gaseous, mobile, and chemically accessible. Silicon's equivalent compound is silicon dioxide, silica, quartz, sand, rock. When silicon burns with oxygen, it forms a solid. This solid is extremely stable, nearly insoluble in water, and chemically unreactive under normal conditions. An organism that metabolizes silicon and oxygen the way Earth organisms metabolize carbon and oxygen would accumulate solid mineral waste inside its body, or would need to excrete sand. The waste products of silicon metabolism cannot easily be transported in fluids, cannot be exhaled as gas, and cannot be recycled through environmental cycles the way carbon dioxide can. This fundamental difference makes silicon-oxygen chemistry poorly suited for biochemistry on worlds with oxygen-rich atmospheres and liquid water. However, removing oxygen from the equation changes the possibilities dramatically. In environments where oxygen is absent or rare, silicon chemistry behaves very differently. Silicon forms stable bonds with hydrogen, creating silanes, molecules analogous to hydrocarbons, but with silicon replacing carbon. The simplest silane is silane itself, with one silicon atom bonded to 4 hydrogen atoms, analogous to methane. Longer chains are possible: disilane with 2 silicon atoms, trisilane with 3, and so on. These silicon-hydrogen chains are reactive and unstable compared to carbon-hydrogen chains, but in the absence of oxygen, they might persist long enough to serve biological functions. Temperature plays a crucial role in silicon chemistry. At Earth's surface temperatures, silicon-silicon bonds are relatively weak compared to carbon-carbon bonds. Silicon compounds tend to break apart more easily, making long, stable silicon chains difficult to maintain. But at much colder temperatures, the kinds found in the outer solar system, silicon chemistry becomes more favorable. Chemical reaction rates slow down dramatically at low temperatures, which could actually help stabilize silicon compounds that would rapidly decompose at room temperature. Meanwhile, some of the alternative solvents that might replace water at these temperatures could interact with silicon compounds in ways that favor complex chemistry. Liquid methane and ethane, which exist naturally on Saturn's moon Titan at temperatures around -180 degrees Celsius, represent one possibility. In these hydrocarbon seas, water is as hard as rock and oxygen is locked away in ice and minerals. Silicon compounds might dissolve in liquid hydrocarbons more readily than in water, and without oxygen to react with, silicon could potentially form the complex, diverse molecules that life requires. The chemistry would be radically different from Earth's biochemistry. Reaction rates would be thousands of times slower, molecules would have different shapes and properties, and the fundamental mechanisms of energy storage and information transfer would need to be reimagined. But the basic requirements for life, complex molecules that can store information, catalyze reactions, and self-replicate, might still be achievable with silicon as the central element. Liquid nitrogen, which exists at even colder temperatures, offers another potential solvent. Nitrogen becomes liquid at -196 degrees Celsius at Earth atmospheric pressure. A world with lakes or oceans of liquid nitrogen would be incomprehensibly cold by Earth standards, but chemical reactions would still occur, just very slowly. Silicon compounds might be more stable and diverse at these extreme temperatures, allowing them to form the kinds of complex structures that life needs. Another approach to silicon-based life involves thinking beyond complete replacement of carbon. Instead of imagining organisms built entirely from silicon, consider hybrid biochemistries that use both elements. Silicon might form structural components, while carbon handles information storage and catalysis. Silicon-oxygen minerals could serve as skeletal elements, providing rigid support structures that carbon-based soft tissues attach to. This is essentially what Earth organisms do. Bones, shells, and the glass-like structures of diatoms all incorporate silicon compounds, though the fundamental biochemistry remains carbon-based. A true silicon-based organism would integrate silicon more deeply into its biochemistry, perhaps using silicon-containing molecules for energy storage, membrane structure, or even genetic material. The information storage challenge represents one of the most significant hurdles for silicon-based life. DNA and RNA work remarkably well as information storage molecules because they're stable enough to preserve information over time, but flexible enough to be copied and modified. The sugar phosphate backbone provides structural support, while the nitrogen bases store actual information through their sequence. Could silicon replace the carbon in the sugar molecules? Silicon-containing analogues of sugars and nucleotides have been synthesized in laboratories, demonstrating that such molecules can exist. Whether they could reliably store and transmit information across generations in a living organism remains unknown, but the chemistry doesn't appear to forbid it outright. Energy metabolism in silicon-based organisms presents another puzzle. Earth organisms primarily extract energy by rearranging chemical bonds, breaking bonds in food molecules, and forming new bonds in waste products, capturing the released energy in the chemical bonds of ATP. Silicon-based organisms would need analogous processes. Perhaps they could oxidize silanese to release energy, though the solid silicon dioxide waste product would be problematic. Or they might use entirely different metabolic pathways based on silicon's interaction with halogens like fluorine or chlorine, creating different waste products that could be more easily managed. In extremely cold environments, metabolic rates could be extraordinarily slow. A silicon-based organism might take years to grow or reproduce, operating on timescales that would make watching grass grow seem rapid by comparison. The evolution of silicon-based life would require a planet with very specific conditions. Silicon would need to be available in reactive forms rather than locked into stable minerals. The temperature would probably need to be very cold to favor silicon chemistry over its tendency to decompose. Oxygen would need to be absent or rare to prevent silicon from forming insoluble silicon dioxide. A suitable solvent other than water would need to exist: liquid hydrocarbons, liquid ammonia, or something even more exotic. These conditions might exist on certain moons in the outer solar system, on rogue planets drifting through interstellar space, or on exoplanets orbiting dim red dwarf stars, where temperatures never rise above the freezing point of water. Titan, with its lakes of liquid methane and ethane, its thick nitrogen atmosphere, and its extremely cold temperatures, represents perhaps the best candidate in our solar system for silicon-based life. NASA's Dragonfly mission, scheduled to launch in the late 2020s, will explore Titan's surface and could potentially detect signs of exotic biochemistry if it exists. The mission won't specifically look for silicon-based life. Nobody knows exactly what signatures such life would produce, but it will analyze organic chemistry in Titan's lakes and atmosphere, searching for patterns that might indicate biological processes. Even if silicon-based life exists nowhere in the universe, studying the possibility expands our understanding of chemistry's relationship to biology. It forces us to question our assumptions about what life requires and what forms it might take. Every element brings different properties, different strengths and weaknesses, different possibilities and constraints. Carbon happened to be the element that worked on Earth under Earth's conditions, but Earth represents just one set of conditions among countless possibilities across the universe. The theoretical possibility of silicon-based life also highlights a challenge in searching for extraterrestrial life. Most of our detection methods assume life will be similar to Earth's, producing oxygen, methane, or other gases we associate with biological activity, building structures we would recognize using chemistry we understand. But silicon-based life operating in liquid methane seas at -180 degrees Celsius would produce completely different signatures. It might metabolize compounds we consider inert waste products and excrete substances we consider essential for life. Its waste products might be our nutrients, and vice versa. We might look directly at a world covered in silicon-based organisms and not recognize it as inhabited because we're searching for carbon signatures. Silicon-based life might be possible in environments so different from Earth that the very definition of life becomes strained. Perhaps silicon-based entities would be better described as self-organizing chemical systems rather than organisms in any sense we would recognize. They might grow and reproduce on timescales of centuries. Their metabolism's so slow that a single thought, if they think at all, might take years to form. They might not have discrete bodies with clear boundaries between self and environment, but instead exist as diffuse networks of silicon-based chemistry spread across vast areas. They might not die in any meaningful sense, but simply cease maintaining organization and gradually disperse back into their environment. Why silicon-based life forms might be possible comes down to chemistry being flexible, creative, and opportunistic. The laws of chemistry operate everywhere in the universe, but they produce different outcomes under different conditions. Silicon's chemical properties give it potential as a basis for complex, self-organizing systems under the right circumstances. Circumstances that apparently don't exist on Earth, but might exist elsewhere. From the hydrocarbon lakes of Titan to hypothetical ice worlds, orbiting dim stars to environments we haven't yet imagined, silicon might be constructing molecules, storing information, and powering metabolisms in ways that parallel carbon-based life, just enough to recognize as living while remaining alien enough to challenge everything we thought we knew about biology, proving that life's possibilities extend beyond the single example we know to encompass chemistries as diverse as the cosmos itself. Why nothing can go faster than light. Light moves at exactly 300,000 kilometers per second in a vacuum, fast enough to circle Earth more than 7 times in a single second. This speed seems arbitrary at first, just another number to memorize. But the speed of light represents something far more profound than a mere velocity. It's a fundamental limit built into the structure of the universe itself, a cosmic speed limit that nothing with mass can reach, let alone exceed. Understanding why nothing can go faster than light means understanding one of the most revolutionary insights in physics, that space and time are not separate, unchanging backdrops to events, but are woven together into a unified fabric that behaves in deeply counterintuitive ways. Before Albert Einstein published his special theory of relativity in 1905, most physicists assumed that velocities simply added together in straightforward ways. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, then someone standing beside the tracks would see the ball moving at 70 kilometers per hour. This common sense addition of velocities works perfectly well at everyday speeds. But Einstein realized that this intuitive picture breaks down at velocities approaching the speed of light, and the breakdown reveals something fundamental about the nature of space and time. Einstein started with 2 basic principles. First, the laws of physics should be the same for everyone moving at constant velocity, regardless of how fast they're going. This principle of relativity had been around since Galileo, and it accords with common experience. You can't tell from experiments done inside a smoothly moving train whether the train is moving or the station is moving past you. Second, and more radically, Einstein proposed that the speed of light is the same for everyone, regardless of how fast they're moving or how fast the light source is moving. This second principle contradicts our everyday intuition about velocity addition. If you're on a train moving forward and you shine a flashlight forward, you might expect someone on the platform to measure the light going faster than someone on the train would measure it, by an amount equal to the train's speed. But experiments repeatedly showed that this doesn't happen. The person on the platform and the person on the train both measure exactly the same speed for the light. This bizarre result seems impossible if we assume that space and time are absolute and unchanging. Einstein's breakthrough was realizing that space and time must not be absolute. Instead, they must adjust themselves to keep the speed of light constant for all observers. When you move faster, time actually slows down for you relative to someone standing still, and distances contract in your direction of motion. These effects, called time dilation and length contraction, are not optical illusions or measurement errors. They're real physical changes in how time flows and how space extends. At everyday speeds, these relativistic effects are incredibly tiny, too small to notice. A person traveling in a car at highway speed experiences time flowing more slowly than someone standing still, but the difference amounts to only billionths of a second over a lifetime. But as speeds approach the speed of light, these effects become dramatic. At 90% of light speed, time runs at only about 44% of the normal rate. At 99% of light speed, time runs at about 14% of normal. As you get closer and closer to light speed, time slows down more and more dramatically, approaching a complete stop as velocity approaches the speed of light. This time, dilation has been confirmed through countless experiments. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground, by exactly the amount Einstein's equations predict. Particles called muons, created when cosmic rays strike the upper atmosphere, live for only about 2 microseconds before decaying. At the speeds they travel, close to the speed of light, time dilation extends their lifetimes enough that they reach the ground before decaying, something that would be impossible if time flowed normally for them. GPS satellites must account for relativistic time dilation, both from their speed and from Earth's gravity, or they would accumulate errors of several kilometers per day. Length contraction is equally real. A spaceship traveling at 99% of light speed would be compressed to about 14% of its rest length in the direction of motion from the perspective of someone watching it pass by. From the crew's perspective, inside the ship, they wouldn't feel compressed. They would measure their ship as having its normal length, but they would measure the distance to their destination as being contracted, appearing much shorter than it does to someone at rest relative to the destination. These strange effects arise from the fact that the speed of light must be the same for everyone. If you're chasing a beam of light at 99% of light speed, you still measure that light beam as moving away from you at full light speed, not at 1% of light speed, as you might expect. This only makes sense if time is flowing more slowly for you, and distances are contracted in your reference frame. The adjustments exactly compensate to keep the speed of light constant. But what happens if you try to accelerate something to light speed? Here's where the cosmic speed limit becomes absolute. As an object with mass accelerates, it gains kinetic energy. In classical physics, kinetic energy depends on velocity in a simple way. Double the velocity, and kinetic energy increases by a factor of 4. But Einstein showed that the relationship changes as you approach light speed. The energy required to accelerate an object increases more and more dramatically as velocity increases, and as you approach light speed, the energy required approaches infinity. This happens because of something called relativistic mass increase. As an object moves faster, it becomes harder to accelerate. It behaves as if it's getting more massive. At 90% of light speed, an object has about twice its rest mass. At 99%, it has about 7 times its rest mass. As velocity approaches light speed, the relativistic mass approaches infinity. To actually reach light speed would require infinite energy to accelerate infinite mass, a physical impossibility. Light itself travels at light speed because photons, the particles of light, have no mass. Maxwell's equations, which describe how electromagnetic fields behave, predict that electromagnetic waves travel at a specific speed determined by properties of space itself. Einstein realized that this speed is the cosmic speed limit, and that massless particles must travel at exactly this speed. Photons don't have to accelerate to light speed. They're created already moving at light speed, and they can never slow down or stop as long as they exist. Other massless particles like gluons, which carry the strong nuclear force, also travel at light speed. Gravitational waves, ripples in space-time itself, travel at light speed as well. Mass is what prevents particles from reaching this ultimate speed. Any particle with mass can approach light speed arbitrarily closely if given enough energy, but can never quite reach it. The relationship between energy, mass, and velocity is captured in Einstein's famous equation E=mc², though this is actually a special case of a more general equation. The full equation shows that total energy equals the rest mass energy plus kinetic energy, and as velocity increases, more and more of the total energy goes into the kinetic energy component. At very high velocities, most of the energy is kinetic rather than rest mass. Particle accelerators demonstrate these principles directly. The Large Hadron Collider accelerates protons to more than 99.99% of light speed. At these velocities, the protons have about 7,000 times more energy than their rest mass energy. Accelerating them to even higher velocities, getting closer to light speed, requires exponentially more energy for each incremental increase in velocity. No matter how much energy you put in, the protons never quite reach light speed, and the energy required to actually reach it would be infinite. Some people wonder whether traveling faster than light might be possible by warping space rather than moving through it. General relativity does allow for exotic spacetime geometries, like wormholes or warp drives, that could theoretically allow effective faster-than-light travel without actually moving through space faster than light. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical way to contract space in front of a spacecraft and expand it behind, allowing the spacecraft to effectively travel faster than light while locally moving slower than light relative to the space immediately around it. However, these solutions require exotic matter with negative mass or negative energy density, properties never observed and possibly forbidden by quantum mechanics. Even if such matter could exist, the energy requirements would be astronomical, potentially requiring more energy than exists in the entire observable universe. These remain purely theoretical concepts, with no practical pathway to implementation, and they don't violate the fundamental principle that nothing can move through space faster than light. The cosmic speed limit has profound implications for space travel. Even at light speed, it would take over 4 years to reach the nearest star beyond our Sun, Proxima Centauri. Travelling to the centre of our galaxy would take over 25,000 years at light speed. Reaching nearby galaxies would take millions of years. The vast distances between stars and galaxies, combined with the absolute speed limit, mean that interstellar travel remains extraordinarily challenging even in principle. For travellers moving at near light speeds, time dilation provides a partial solution. From the crew's perspective, a journey might take only months or years, while decades or centuries pass on Earth. This time dilation allows relativistic travellers to cross vast distances within their own lifetimes, though everyone they knew would age far more or be long dead by the time they returned. This creates a fundamental asymmetry. The traveller's time and the stay-at-home's time flow at different rates, and there's no way to make them match up again. The speed of light also limits how quickly information can travel. When you see a star in the night sky, you're seeing it as it was years or centuries ago. That's how long the light took to reach you. The sun you see is 8 minutes in the past. If the sun suddenly vanished, we wouldn't know for 8 minutes. This light travel time creates what physicists call a light cone, the boundary between events that can influence you and events that cannot because they're too far away in space and too close in time for light to have travelled from there to here. Causality itself depends on the cosmic speed limit. If information could travel faster than light, it would be possible to send messages backward in time, to communicate with your own past. This creates logical paradoxes, like sending a message to your past self, telling yourself not to send the message. The speed of light limit prevents these paradoxes by ensuring that cause always precedes effect for all observers, regardless of their motion. The universe seems designed in a sense with this speed limit built in. Light speed isn't just the speed at which light happens to travel, it's a fundamental property of space-time itself, woven into the structure of reality. Mass is what prevents particles from reaching this ultimate speed, and the closer you get to it, the more energy is required to go faster, asymptotically approaching infinite energy at the limit. This speed limit connects space and time in an intimate way. Space and time aren't separate entities but are aspects of a unified, four-dimensional space-time. Events that appear simultaneous to one observer might not be simultaneous to another observer moving differently. The cosmic speed limit defines the structure of this space-time, determining how space and time mix together as observers change velocity. Why nothing can go faster than light ultimately comes down to the structure of space-time itself. The speed of light isn't a speed limit in the sense of a rule imposed from outside. It's a fundamental property of how the universe is built, how space and time relate to each other, and how energy and mass behave. Reaching light speed would require infinite energy. The only things that can travel at light speed are things with no mass, like photons, which must always travel at this speed. Everything else, everything with mass, can only approach this ultimate velocity, forever accelerating, but never quite reaching the cosmic speed limit that defines the maximum rate at which anything can travel through the fabric of spacetime. Why alien life might be microscopic. When we imagine alien life, our minds often conjure images of intelligent beings piloting spacecraft, complex organisms with eyes and limbs exploring alien landscapes, or at minimum, creatures we could observe and recognize as alive. But this expectation might be profoundly misguided. Earth's history offers a sobering perspective. For roughly 3 billion of the 4 billion years that life has existed on our planet, all organisms were microscopic. Bacteria, archaea, and single-celled eukaryotes dominated Earth's biosphere for the vast majority of life's history. Complex multicellular organisms, plants, animals, fungi, are recent arrivals, having existed for less than 1 billion years. If Earth's timeline is any indication, most life in the universe might be microscopic, existing as single cells or simple colonies that never evolve into the complex macroscopic forms we're accustomed to seeing. The transition from single cell to multicellular life represents one of the most difficult evolutionary innovations in Earth's history. It only happened once in the bacterial lineage, never successfully transitioning beyond simple filaments and colonies, and only a few times in the eukaryotic lineage, producing plants, animals, and fungi. This rarity suggests that while single-celled life might emerge relatively easily wherever conditions permit, the evolution of complex multicellularity requires specific circumstances that might not commonly occur. Many alien worlds might develop thriving microbial biospheres that remain forever microscopic because the evolutionary innovations needed for large, complex organisms never occur. Energy availability represents the first major constraint on complexity. Complex multicellular organisms require substantial energy to build and maintain their bodies. They need energy to power specialized organs, to move through their environments, to grow to large sizes. Most of this energy ultimately comes from oxygen-based metabolism, which releases far more energy per molecule of food than anaerobic metabolism does. The efficiency of oxygen metabolism, about 15 times more energetic than the best anaerobic alternatives, enabled the evolution of large active organisms on Earth. But oxygen was not always available in Earth's atmosphere. For the first 2 billion years or more of life's existence, the atmosphere contained very little free oxygen. Life during this time remained entirely microscopic and relatively simple, constrained by the low energy yields of anaerobic metabolism. Only after photosynthetic bacteria evolved and began producing oxygen as a waste product did atmospheric oxygen accumulate, and only after oxygen reached substantial levels could organisms evolve the high-energy metabolisms necessary for large size and complexity. Many alien worlds might never undergo this transition. If photosynthetic life never evolves, or if it evolves but produces different waste products, perhaps using electron donors other than water that don't release oxygen, the atmosphere might remain oxygen-poor indefinitely. Life on such worlds would be permanently restricted to anaerobic metabolism, with its inherent energy limitations preventing the evolution of large complex organisms. The biosphere might flourish with countless microscopic species filling every available niche, but nothing larger than perhaps a millimeter would ever evolve, because the energy budgets of anaerobic metabolism cannot support larger sizes or more complex structures. Predation drives much of the evolution toward complexity on Earth. The development of predators created selection pressure for prey to evolve defenses, armor, toxins, multicellularity that makes them too large to be consumed by single-celled predators. Predators, in turn, evolved mechanisms to overcome these defenses: better sensing systems, faster movement, cooperative hunting. This evolutionary arms race between predators and prey drove increasing complexity, with both sides becoming more sophisticated over generations. The transition to multicellularity in animals might have been driven at least partially by predation pressure from other single-celled organisms. On an alien world where predation never becomes significant, perhaps because environmental conditions don't favor the evolution of heterotrophs, or because chemical energy is so abundant that organisms don't need to consume each other, this driver of complexity would be absent. Life might remain a collection of bacteria-like organisms metabolizing chemicals from their environment, with no selection pressure favoring the evolution of larger, more complex forms. Without predation or competition driving an evolutionary arms race, the biosphere might reach an equilibrium of simple, efficient microorganisms that persist unchanged for billions of years. The evolution of eukaryotic cells, cells with nuclei and complex internal structures, required an extraordinarily unlikely event called endosymbiosis, where one cell engulfed another, and instead of digesting it, established a permanent symbiotic relationship. On Earth, mitochondria, the energy-producing organelles in eukaryotic cells, originated as free-living bacteria that were engulfed by other cells and eventually became integrated parts of those cells. This event, which happened roughly 2 billion years ago, was apparently unique in Earth's history. It happened once, and all eukaryotic cells descend from that single event. Eukaryotic cells made complex multicellular life possible. Their mitochondria provide far more energy per cell than bacteria can generate, allowing cells to support larger genomes and more complex structures. Their internal compartmentalization allows specialized biochemistry to occur in different cellular regions. Their complex cytoskeletons enable intricate cell shapes and coordinated movements. Without eukaryotic cells, complex multicellular organisms probably could not evolve. If endosymbiosis was difficult, requiring very specific circumstances to occur even once on Earth, alien worlds might never undergo this transition. Life might remain forever bacterial, lacking the cellular complexity necessary as a foundation for multicellular organisms. These worlds would have rich microbial ecosystems with tremendous diversity at the microscopic level, but would never produce organisms visible to the naked eye. Environmental stability influences evolutionary innovation. Earth's environment has been highly variable over geological time. Ice ages, warming periods, asteroid impacts, volcanic catastrophes, changing atmospheric composition, continents drifting and colliding. These environmental changes created selection pressures that favored adaptability and innovation. Mass extinctions wiped out dominant groups, allowing new forms to radiate and diversify. Without such disruptions, dominant organisms might remain unchanged indefinitely, never facing circumstances that favour more complex alternatives. An alien world with a remarkably stable climate and environment over billions of years might never see complex life evolve. Early microbial ecosystems might reach an equilibrium where existing organisms are so well adapted to unchanging conditions that no complex innovations provide advantages. Microbes would efficiently fill every niche, processing every available chemical, extracting every erg of available energy, and no evolutionary pressure would favour the metabolically expensive transition to larger, more complex forms. The planet would remain microbial forever, not because complex life is impossible, but because stable conditions never create circumstances where complexity is advantageous. The availability of ecological niches affects diversification. On Earth, new environmental niches continuously opened as continents drifted, climates changed, and oxygen accumulated in the atmosphere. Moving onto land created entirely new sets of niches, terrestrial environments with different challenges than aquatic ones. Flying created another set of niches. Each new opportunity drove adaptive radiations where organisms evolved to exploit newly available resources and habitats. A planet lacking this niche diversity might not provide opportunities for complex life to evolve. A world completely covered by ocean with no land would lack terrestrial niches. A world with a homogeneous environment, perhaps a global ocean with uniform temperature and chemistry from pole to pole, would offer fewer distinct niches than Earth's highly varied environments. With fewer niches available, there would be less opportunity for adaptive radiation and less selection pressure driving organisms toward the specializations and complexities that fill diverse ecological roles. Timescales matter significantly. Evolution proceeds through random mutations and natural selection, accumulating beneficial changes over countless generations. Complex innovations require many individual evolutionary steps, each one building on previous changes. The evolution of eyes, for instance, required the initial evolution of light-sensitive proteins, then the gathering of these proteins into light-sensitive patches, then the invagination of these patches into cups that provide directional information, then the development of lenses that focus light, then the neural processing systems to interpret visual information. Each step took many generations and many mutations. On an alien world where organisms have very long generation times, perhaps living for thousands of years before reproducing, evolution would proceed extraordinarily slowly. A complex innovation that might evolve in tens of millions of years on Earth, where many organisms reproduce annually or even faster, might take billions of years on a world where generation times are measured in millennia. If the planet star has a relatively short lifetime, perhaps a massive star that will exhaust its fuel in a few billion years, there might simply not be enough time for complex life to evolve before the star's death sterilizes the planet. The chemical environment limits biological complexity. Complex organisms require diverse biochemistry, proteins for structure and catalysis, lipids for membranes, nucleic acids for information storage, carbohydrates for energy and structure. Building these diverse molecules requires access to various elements in appropriate forms. A planet poor in essential elements, perhaps lacking sufficient phosphorus, nitrogen, sulfur, or trace metals, might not provide the chemical building blocks necessary for complex biochemistry. Life might arise using simpler chemistry, but might be unable to evolve the molecular diversity needed for complex cells and multicellular structures. Physical constraints on size affect what complexity is possible. Surface tension becomes increasingly important at small scales. For microscopic organisms living in water, surface tension is a significant force. Water behaves more like thick syrup than like the thin fluid humans experience. Moving through water at microscopic scales requires different strategies than swimming at macroscopic scales. These physical differences mean that microorganisms experience a fundamentally different physical world than large organisms, and the adaptations that work well at microscopic scales might not scale up successfully. The speed of light sets absolute limits on how quickly information can be transmitted within an organism. For microscopic cells, this is never a constraint. Signals cross the cell in negligible time. But as organisms grow larger, signal transmission times become significant. A 1-meter organism experiences light travel times of about 3 nanoseconds, still essentially instantaneous for chemical and neural signals. But organisms must coordinate their parts, and this coordination becomes more difficult as size increases. Neural signals in humans travel at speeds of about 100 meters per second, meaning signals take milliseconds to travel from extremities to brain. For a hypothetical organism many meters or kilometers in size, coordination would become increasingly difficult. Detection bias affects our perception of what life looks like. Humans evolved to perceive objects roughly our own size. We see animals, plants, and landscape features easily because our sensory systems are optimized for that scale. Microscopic organisms are invisible without technological assistance. An alien observer visiting Earth equipped with sensing systems similar to human vision might conclude that Earth has relatively little life, missing entirely the vast microbial world that actually dominates in terms of biomass, diversity, and metabolic activity. Similarly, when we search for alien life, our methods tend to focus on detecting macroscopic effects: oxygen in atmospheres produced by photosynthetic organisms, changes in planetary albedo from vegetation, perhaps even artificial lights from technological civilizations. A planet covered in microbial life, producing no oxygen, with no multicellular organisms, with nothing visible at planetary scales, might appear lifeless to our telescopes, even if it hosts an incredibly rich and diverse microbial biosphere. Statistical considerations based on Earth's history suggest that if we discovered alien life, it would most likely be microscopic. Life existed on Earth for about 3 billion years before complex multicellular organisms evolved. If we randomly selected a moment in Earth's history, there would be a roughly 75% chance of finding only microscopic life. Assuming Earth's timeline is typical, which may or may not be true, most inhabited planets at any given time would be in their microbial phase, with complex life being relatively rare. Why alien life might be microscopic comes down to microbial life being easy to achieve relative to complex life, requiring only basic metabolism, reproduction, and evolution, while complex life requires numerous specific evolutionary innovations: oxygenic photosynthesis or equivalent high-energy metabolism, eukaryotic cells with their mitochondrial endosymbionts, multicellularity with coordinated cells working together, specialized tissues and organs, each one potentially rare or slow to evolve. Many worlds might develop thriving microbial ecosystems within their first billion years, but might never progress beyond that stage, remaining forever inhabited by bacteria-like organisms invisible to the naked eye, yet representing the most common form of life in the universe. A cosmos filled not with civilizations or even visible organisms, but with countless worlds hosting microbial biospheres that flourish in every conceivable environment, from sunlit surface waters to deep subsurface rocks, from hydrothermal vents to subsurface oceans beneath ice, each microscopic cell representing a success story of evolution in its own right, reminding us that complexity and large size are not prerequisites for biological success, and that if we ever detect life beyond Earth, we should not be disappointed if it consists of nothing more than microbes, because microbial life might be life's most common, most successful, most enduring form across the vast expanse of the living universe. Why distant galaxies? Look red. When astronomers point their most powerful telescopes toward the deepest reaches of space, photographing galaxies billions of light years away, they notice something remarkable. These distant galaxies appear distinctly redder than nearby ones. Light that was emitted as ultraviolet or blue has been shifted toward red and infrared wavelengths by the time it reaches Earth. This redshift is one of the most important observations in all of astronomy, providing direct evidence for the expansion of the universe and allowing astronomers to measure cosmic distances and trace the history of the cosmos back nearly to the Big Bang itself. The primary cause of this reddening is cosmological redshift, a consequence of the universe's expansion. This phenomenon was first observationally established by Edwin Hubble in 1929, though the theoretical groundwork had been laid by several physicists, including Alexander Friedmann and Georges Lemaitre, who independently developed solutions to Einstein's equations of general relativity that predicted an expanding universe. Hubble observed that distant galaxies showed spectral lines, the characteristic fingerprints of elements absorbing or emitting light at specific wavelengths, shifted toward longer, redder wavelengths. Moreover, he found that more distant galaxies showed larger redshifts, establishing what became known as Hubble's law. The recession velocity of a galaxy is proportional to its distance. The expansion of the universe is not like objects moving through space. It's space itself that's expanding. Imagine the universe as the surface of a balloon with galaxies painted on it. As you inflate the balloon, the surface stretches and the distance between any 2 points on the surface increases. The galaxies themselves don't move through the rubber. The rubber itself expands, carrying the galaxies apart. This is fundamentally different from regular motion through space, and it's this expansion of space that creates cosmological redshift. When a galaxy emits light, that light begins its journey through space toward Earth. The light consists of electromagnetic waves, oscillating electric and magnetic fields propagating through space. As the light travels, the space through which it's traveling is expanding. This expansion stretches the wavelength of the light. Imagine a wave painted on a rubber band. If you stretch the rubber band, the wave gets stretched too, its wavelength increasing. The same thing happens to light traveling through expanding space. Light that began as ultraviolet with a wavelength of 300 nanometers might arrive at Earth as visible red light with a wavelength of 600 nanometers if it has traveled through enough expanding space. The amount of redshift depends on how much the universe has expanded during the light's journey. Astronomers quantify this using the redshift parameter, represented by the letter Z. A redshift of Z equals 1 means the universe has doubled in size since the light was emitted. Wavelengths have stretched by a factor of 2. A redshift of Z equals 2 means the universe has tripled in size. Wavelengths have stretched by a factor of 3. The highest redshift galaxies yet observed have redshifts around Z equals 13 to 14, meaning the universe has expanded by a factor of about 14 or 15 since those galaxies emitted the light we now detect. These galaxies existed when the universe was only a few 100 million years old, less than 3% of its current age. For nearby galaxies, the redshift is small, perhaps Z equals 0.01 or less. The Andromeda galaxy, our nearest large galactic neighbour, actually shows a blue shift rather than a red shift, because it's moving toward us through space faster than the cosmic expansion is carrying it away. But for galaxies more than a few 100 million light-years distant, cosmological redshift dominates, and the farther the galaxy, the larger the redshift. This relationship between distance and redshift allows astronomers to use redshift as a distance indicator. By measuring the redshift of spectral lines in a galaxy's light, they can calculate how far away it is and how long ago the light was emitted. A galaxy at Z equals 1 is seen as it was about 8 billion years ago, when the universe was roughly half its current age. A galaxy at Z equals 6 is seen as it was less than 1 billion years after the Big Bang, when the universe was still in its infancy and the first generations of stars were forming. Redshift affects all wavelengths equally, in terms of the stretching factor. Ultraviolet light gets stretched into visible light. Visible light gets stretched into infrared. Infrared gets stretched into far infrared and eventually into microwaves. For the most distant galaxies, light that was emitted in the ultraviolet, the signature of hot, young stars, arrives at Earth as infrared radiation. This is why infrared telescopes, like the James Webb Space Telescope, are so valuable for studying the early universe. They can detect the stretched light from the most distant galaxies, galaxies so far away that their visible light has been redshifted entirely out of the visible spectrum. There's another related effect that makes distant galaxies appear redder beyond just the stretching of wavelengths. As light loses energy through redshift, longer wavelengths mean lower energy. The apparent brightness of the galaxy dims. A galaxy at high redshift appears fainter than it would if there were no cosmic expansion. Additionally, the rate at which photons arrive is reduced. If a galaxy emits 1 photon per second toward Earth, but the universe doubles in size during the light's journey, those photons arrive spread out over 2 seconds because the space between them has been stretched. This reduces the detected brightness even further. The cosmic microwave background radiation provides the most extreme example of cosmological redshift. This radiation was emitted when the universe was 380,000 years old, at a temperature of about 3,000 Kelvin. At that temperature, matter emitted primarily visible and infrared radiation. The redshift since that time is about C equals 1,100, meaning the universe has expanded by a factor of 1,100. Wavelengths have been stretched by the same factor, so light that was visible orange or red has been stretched into microwave radiation. The temperature corresponding to this radiation has dropped by the same factor, from 3,000 Kelvin down to 2.7 Kelvin today. It's important to distinguish cosmological redshift from Doppler shift, though they're related and can sometimes be confused. Doppler shift occurs when a light source moves through space toward or away from an observer. An approaching object's light is blue shifted, compressed to shorter wavelengths, while a receding object's light is redshifted. This is the effect that changes the pitch of a siren as an ambulance approaches and then passes you. For galaxies with relatively small redshifts, say Z less than 0.1, cosmological redshift and Doppler shift give nearly identical results and can be treated interchangeably for many purposes. But for high redshifts, the distinction matters. Cosmological redshift is fundamentally about the expansion of space itself, while Doppler shift is about motion through space. Redshift also allows astronomers to study the history of cosmic expansion. By measuring redshifts of many galaxies at various distances and determining their distances through other methods, like standard candles, objects of known intrinsic brightness, astronomers can trace how the expansion rate has changed over cosmic history. These studies revealed one of the most surprising discoveries in modern cosmology. The expansion of the universe is accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery, made by studying distant supernovae and measuring how their redshifts and distances deviated from what would be expected in a universe with constant or decelerating expansion. The acceleration implies the existence of dark energy, a mysterious component that makes up about 68% of the universe's total energy density and exerts a kind of repulsive effect that pushes space apart. This dark energy's influence has grown over cosmic time as the universe expanded and matter became more dilute. In the early universe, matter dominated and the expansion was slowing down. But a few billion years ago, dark energy became dominant and the expansion began accelerating. distant galaxies' redshifts encode this history, showing patterns that reveal when the transition from deceleration to acceleration occurred. Redshift measurements also reveal structure in the universe. When astronomers measure redshifts for thousands or millions of galaxies, they can create three-dimensional maps showing how galaxies are distributed in space. These maps reveal the cosmic web, the filaments, walls, and voids that constitute the large-scale structure of the universe. Regions where galaxies are closely spaced show similar redshifts because they are at similar distances. Voids show up as redshift ranges where few galaxies appear. The chemical evolution of the universe is written in redshift as well. Spectroscopy of distant galaxies reveals what elements were present when that light was emitted billions of years ago. By comparing galaxies at different redshifts, different cosmic times, astronomers can trace how the abundance of heavy elements has increased over cosmic history as successive generations of stars created these elements through nuclear fusion and dispersed them through supernova explosions. Galaxies at Z equals 6 or 7 show much lower abundances of elements heavier than helium compared to nearby galaxies, confirming that the early universe was primarily hydrogen and helium, with heavy elements accumulating over billions of years. Even the shapes and types of galaxies change with redshift. High redshift galaxies tend to be smaller, more irregular, and more actively forming stars than low redshift galaxies. This reveals that galaxies evolve over time, growing through mergers and gradually building up their stellar populations. The universe at Z equals 2, when it was about 3 billion years old, was a much more turbulent place, with higher rates of galaxy interactions and star formation than the relatively sedate local universe we see today. Gravitational lensing affects redshift measurements in subtle ways. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity bends the light's path and can magnify the image. But it also affects the light's frequency. Different images of a gravitationally lensed galaxy, formed by light taking different paths around the lensing mass, can show slightly different redshifts due to the gravitational time dilation in the lens's gravitational field. These tiny differences help astronomers probe the distribution of mass in the lensing object. The reddening of distant galaxies is therefore not just an interesting observational fact, but a fundamental window into cosmic history. Every measurement of a galaxy's redshift tells us how far away it is, how long ago its light was emitted, and what the universe was like at that cosmic epoch. The systematic increase in redshift with distance directly demonstrates that the universe is expanding, that it had a beginning in the Big Bang, and that it's evolving over time. The precise pattern of redshifts reveals the expansion history, constrains the properties of dark energy, and allows us to trace the formation and evolution of structure across billions of years of cosmic time, making the reddening of distant galaxies one of the most information-rich phenomena in observational astronomy. Why moons orbit in perfect circles? When you look at diagrams of moons orbiting planets, they're often depicted as perfect circles with the planet at the center. This image is actually misleading. No moon orbits in a perfect circle. Every orbit in the universe, whether it's a moon around a planet around a star, or a star around a galaxy's center, follows an ellipse, a stretched circle with the central body at one of the ellipse's two focal points, not at the center. However, many moon orbits are remarkably close to circular, so nearly circular that the deviation is barely noticeable. Understanding why some moons have nearly circular orbits, while others follow elongated ellipses, means understanding orbital mechanics, tidal forces, and the long-term evolution of gravitational systems. The fundamental laws governing orbital motion were discovered by Johannes Kepler in the early 17th century, based on meticulous observations of planetary positions compiled by Tycho Brahe. Kepler's first law states that planets orbit the Sun in ellipses, with the Sun at one focus. This applies equally to moons orbiting planets. An ellipse is characterized by its eccentricity, a number between 0 and 1. An eccentricity of 0 represents a perfect circle. An eccentricity close to 0 represents a nearly circular ellipse. Higher eccentricities produce more elongated ellipses, and an eccentricity of 1 represents a parabola, an open curve, not a closed orbit at all. Earth's moon has an orbital eccentricity of about 0.0549, meaning its orbit is quite close to circular but noticeably elliptical. At its closest approach, called perigee, the moon is about 363,000 kilometers from Earth. At its farthest point, called apogee, it's about 405,000 kilometers away, a difference of about 42,000 kilometers, or roughly 11%. This variation causes the moon's apparent size in Earth's sky to change noticeably over the course of a month. A full moon at perigee appears about 14% larger in diameter than a full moon at apogee, the so-called supermoon phenomenon. Many other moons have far more circular orbits than Earth's moon. Jupiter's major moons, the Galilean satellites Io, Europa, Ganymede, and Callisto, all have very low eccentricities. Io's eccentricity is about 0.0041, Europa's is 0.009, Ganymede's is 0.0013, and Callisto's is 0.0074. These are remarkably circular orbits, with the differences between closest and farthest approaches being only tiny fractions of the orbital radius. Saturn's largest moon, Titan, has an eccentricity of 0.0288, still quite circular, though less so than Jupiter's major moons. The reason many moons approach circular orbits lies in tidal forces and the dissipation of energy over time. When a moon orbits a planet on an elliptical path, its distance from the planet changes continuously. As the distance changes, so does the strength of the tidal forces between the planet and moon. Tides work both ways. The moon raises tides on the planet, and the planet raises tides on the moon. These tidal bulges require energy to create because they deform the bodies involved, flexing and stretching them. For a moon in an eccentric orbit, the tidal bulges change in size as the moon moves closer to and farther from the planet. This continuous flexing dissipates energy as heat through internal friction, the same mechanism that makes a rubber ball warm up when you repeatedly squeeze and release it. This tidal heating is not a small effect. Jupiter's moon, Io, experiences such intense tidal heating due to its slightly eccentric orbit that it's the most volcanically active body in the solar system, with lava lakes, erupting volcanoes, and a surface constantly renewed by volcanic activity. The energy dissipated through tidal heating doesn't disappear. It comes from the orbital energy of the moon. As orbital energy is lost, the characteristics of the orbit change. Specifically, the eccentricity decreases. The orbit becomes more circular. This process, called tidal circularization, operates on timescales of millions to billions of years, gradually transforming elliptical orbits into nearly circular ones. The timescale depends on the masses involved, the distances, the physical properties of the bodies, how easily they deform, and the initial eccentricity. Earth's moon provides a clear example of tidal evolution, though in the moon's case the effect is primarily in the exchange of angular momentum rather than circularization. The moon raises tides on Earth, the familiar ocean tides that rise and fall twice daily. Earth's rotation carries these tidal bulges slightly ahead of the Earth-Moon line because of friction and the time it takes for water to respond to the tidal forces. This offset means the tidal bulges pull on the moon, accelerating it in its orbit and causing it to gradually move away from Earth at about 3.8 centimeters per year, a rate precisely measured by bouncing laser beams off retroreflectors left on the moon by Apollo astronauts. As the moon moves outward, Earth's rotation slows down to conserve angular momentum. Earth's day gradually lengthens, currently by about 1.7 milliseconds per century. This process has been operating for billions of years. Early in Earth's history, when the moon was much closer, tidal forces were far stronger. Days were much shorter, perhaps only 5 to 6 hours, and the moon orbited much faster and on a more eccentric orbit. Over billions of years, tidal forces circularized the moon's orbit to its current low, but non-zero eccentricity. The moon's orbital eccentricity isn't zero because the circularization process hasn't completed and perhaps never will. The sun's gravitational pull perturbs the moon's orbit, periodically increasing its eccentricity slightly. These perturbations compete with the tidal circularization, creating a balance that maintains a small but non-zero eccentricity. Additionally, the ultimate end state of tidal evolution is tidal locking, where the moon always shows the same face to the planet, and the planet's rotation period equals the moon's orbital period. Earth's moon is already tidally locked to Earth, but Earth is not locked to the moon. Eventually, if given enough time, Earth would become locked to the moon as well, with both bodies always showing the same faces to each other, though this would take tens of billions of years, longer than the sun's remaining lifetime. Some moons maintain eccentric orbits despite tidal forces because of orbital resonances with other moons. Jupiter's moons Io, Europa, and Ganymede are locked in a 1 to 2 to 4 resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This resonance was discovered by Pierre-Simon Laplace in the 18th century. The gravitational interactions in this resonance maintain Io's and Europa's orbital eccentricities even as tidal forces try to circularize them. The result is continuous tidal heating, keeping Io's interior molten and likely maintaining a subsurface ocean on Europa beneath its icy crust. Saturn's moon Enceladus experiences similar effects. Its orbital eccentricity of about 0.0047 seems small, but it's sufficient to generate significant tidal heating in this small moon. Enceladus orbits in a 2-to-1 resonance with the larger moon Dione. The resonance prevents the orbit from fully circularizing, maintaining just enough eccentricity to produce tidal heating that keeps a subsurface ocean liquid beneath Enceladus's southern polar region. Geysers of water erupt through cracks in the ice, spraying material into space and creating Saturn's E-ring. New moons in eccentric orbits take time to circularize. If a moon forms from a giant impact, as Earth's moon likely did, the debris initially orbits in highly eccentric, chaotic paths. Over time, collisions between orbiting fragments dissipate energy and circularize the orbits, while material gradually coalesces into a single moon. The moon starts with a moderately eccentric orbit that gradually becomes more circular through tidal interactions. Young moons should have more eccentric orbits than old moons, all else being equal. Captured moons often retain eccentric orbits. When a planet gravitationally captures a passing asteroid or comet, the capture typically results in a highly eccentric orbit. Without significant tidal forces or atmospheric drag to circularize the orbit, it remains eccentric indefinitely. This is why many of the small, irregular outer moons of the giant planets have highly eccentric orbits. They're captured asteroids, or Kuiper belt objects, that have never undergone significant tidal circularization. Mars's 2 small moons, Phobos and Deimos, are thought to be captured asteroids, though their orbits are fairly circular, suggesting either that they've been in place long enough for tides to act or that they were captured through an unusual mechanism that placed them in nearly circular orbits initially. The mathematical framework for understanding orbital evolution through tides was developed in the 19th and 20th centuries by George Darwin, son of Charles Darwin, and others. The tidal quality factor, denoted Q, quantifies how efficiently a body dissipates tidal energy. Bodies with low Q dissipate energy efficiently, leading to faster orbital evolution. Rocky bodies typically have Q values of 10 to 100. Gas giants have Q values around 10,000 to 100,000 because gases don't maintain permanent tidal bulges as efficiently as solid or liquid bodies. These Q values determine how quickly orbits evolve. Computer simulations of moon system evolution incorporate tidal effects, gravitational interactions between multiple moons, and perturbations from the Sun and other planets. These simulations show that systems naturally evolve toward configurations with circular orbits, tidal locking, and often orbital resonances. The solar system's moon systems we observe today represent billions of years of this evolution, with orbits that have circularized, resonances that have captured moons into stable configurations, and tidal locking that has synchronized rotations. Some moons will never fully circularize their orbits because external perturbations constantly act to increase eccentricity. The moon's orbit around Earth is perturbed by the Sun, creating periodic variations in eccentricity over 27.5-day cycles. Neptune's moon Triton orbits in a retrograde direction, opposite to Neptune's rotation, suggesting it was captured from the Kuiper belt. Triton's orbit has circularized over billions of years to an eccentricity of only 0.000016, one of the most circular orbits known, but the orbit is also slowly decaying. Tidal forces are causing Triton to spiral inward, and in about 3.6 billion years, it will cross Neptune's Roche limit and be torn apart, forming a spectacular ring system. The appearance of circular orbits in diagrams and popular depictions stems from the fact that many major moons genuinely have nearly circular orbits. Eccentricities low enough that drawing the ellipse versus a circle would show barely any difference. For Ganymede, with its eccentricity of 0.0013, the difference between the orbit's longest and shortest diameters is only 0.26%. Drawing this accurately would require extraordinary precision. For practical purposes, these orbits are functionally circular, even though they're technically ellipses. Perfect circles don't exist in orbital mechanics because achieving exactly zero eccentricity requires perfectly balanced initial conditions and no subsequent perturbations. Conditions that never occur in nature. But through billions of years of tidal evolution, many moons have achieved orbits so close to circular that they serve as excellent approximations shaped by the patient, inexorable work of tidal forces, dissipating energy, transforming the chaos of formation into the elegant, nearly circular orbits that characterize mature moon systems throughout the solar system, demonstrating how gravitational interactions over immense timescales can organize and simplify what begins as disorder, creating the stable, predictable, celestial mechanics that allow us to calculate moon positions years or centuries into the future with extraordinary precision. Why gas giants spin at different speeds? The giant planets of our solar system rotate at speeds that seem almost impossible when you first encounter the numbers. Jupiter, the largest planet, completes a full rotation in just under 10 hours. Imagine standing on a world where a single day passes more than twice as fast as the time it takes to watch a long movie. Saturn spins even faster in some ways, though its rotation is more complex. Uranus and Neptune, the ice giants farther out, rotate at their own distinct rates, each with rotational periods that tell a story about how they formed and what has happened to them over billions of years. Picture Jupiter in your mind, a massive sphere of swirling clouds in shades of cream, brown, orange, and red. This giant world contains more mass than all the other planets combined, yet it spins so rapidly that it bulges noticeably at its equator. If you could somehow stand at Jupiter's equator, you would be moving at over 28,000 miles per hour, far faster than anything on Earth except spacecraft. The planet's day, the time it takes to complete one rotation, is only about 9 hours and 55 minutes. This incredible speed creates winds that race around the planet in alternating bands, some flowing eastward, others westward, creating the distinctive striped appearance we see in telescopes. But here's where it becomes fascinating. Not all of Jupiter spins at the same rate. The planet is made primarily of hydrogen and helium in gaseous and liquid forms, with no solid surface to anchor to. The equatorial regions spin slightly faster than the polar regions, completing a rotation in about 5 minutes less time. This differential rotation is possible because Jupiter isn't a rigid body like Earth. Different latitudes can rotate at different speeds, sliding past each other in the fluid interior. The deep interior, where hydrogen is compressed into a metallic liquid state, may rotate at yet another rate, one that scientists are still working to measure precisely. Saturn presents an even more puzzling picture. This ringed giant is less dense than water. If you could find an ocean large enough, Saturn would float. Its rapid rotation, with a day lasting only about 10 hours and 33 minutes, causes an even more pronounced equatorial bulge than Jupiter's. The planet's diameter at the equator is nearly 10% larger than its diameter from pole to pole. Picture a sphere that's been squeezed from the top and bottom while being stretched around its middle, all due to the centrifugal force of its rapid spin. What makes Saturn particularly mysterious is that determining its exact rotation rate has proven remarkably difficult. Unlike rocky planets, which have surface features that can be tracked, or planets with strong magnetic fields that rotate with the deep interior, Saturn presents challenges. Its magnetic field is almost perfectly aligned with its rotation axis, which makes it hard to use as a reference. Different methods of measuring Saturn's rotation have given different results, sometimes varying by as much as several minutes. The planet's atmosphere rotates at different speeds, at different latitudes, just like Jupiter's. But figuring out the rotation rate of Saturn's deep interior, the true rotation rate of the planet, remains one of the ongoing puzzles in planetary science. The rings of Saturn add another layer to this story. These rings are made of countless particles of ice and rock, each one orbiting Saturn independently, according to the laws of orbital mechanics. The inner parts of the rings orbit faster than the outer parts, completely independent of how fast the planet itself spins. If you could watch from above Saturn's North Pole, you would see the rings spinning like a vast flat disk, while beneath them the planet rotates at its own separate rate. And within the planet, different layers rotate at their own speeds as well. Now travel farther out to Uranus, the tilted giant. This planet rolls through space like a ball rolling along the ground, with its axis of rotation tilted 98 degrees from the perpendicular to its orbit. Something in Uranus's past, likely a massive collision with another planet-sized object, knocked it onto its side. Despite this dramatic tilt, Uranus rotates relatively quickly, completing one rotation in about 17 hours and 14 minutes. This is slower than Jupiter and Saturn, but still far faster than Earth's 24-hour day. The interior structure of Uranus affects its rotation in ways different from the gas giants. Uranus is classified as an ice giant rather than a gas giant because, beneath its hydrogen and helium atmosphere, it contains a much larger proportion of water, methane, and ammonia ices. These materials, compressed under tremendous pressure, create a layered interior that may not mix as freely as the interiors of Jupiter and Saturn. This layering could mean that different depths within Uranus rotate at substantially different rates, though our knowledge of the planet's interior remains limited from Earth. Neptune, the farthest giant planet, spins with a period of about 16 hours and 6 minutes, slightly faster than Uranus, despite being similar in size and composition. Neptune's deep blue colour comes from methane in its atmosphere, which absorbs red light and reflects blue. Like the other giant planets, Neptune shows differential rotation, with its equatorial atmosphere moving at a different speed than the atmosphere at higher latitudes. The planet has the strongest winds in the solar system, with some storms showing wind speeds exceeding 1,200 miles per hour. These winds don't simply follow the rotation of the planet. They race around at speeds that are faster than the underlying rotation rate, driven by heat flowing from Neptune's interior. The question of why these giants spin at such different speeds takes us back to the formation of the solar system. Imagine the early solar system as a vast rotating disk of gas and dust surrounding the young sun. Within this disk, material began to clump together, forming the seeds of planets. As these clumps grew larger through gravity, pulling in more material, they began to spin faster due to the conservation of angular momentum, the same principle that causes a figure skater to spin faster when pulling their arms in. Each growing planet accumulated material that was already moving in orbit around the sun. This material had angular momentum, and as it fell onto the growing planet, it transferred that momentum to the planet itself. The amount of spin the planet ended up with depended on exactly how this accretion process occurred, the trajectories of the infalling material, the timing of impacts, and whether the material came in symmetrically or from preferred directions. Jupiter and Saturn, being closer to the Sun and in regions with more available material, grew faster and larger than Uranus and Neptune. Their rapid growth meant they could capture enormous amounts of gas from the protoplanetary disk before it dissipated. This gas fell onto the planets from all directions, and the net effect was to spin the planets up to high rotation rates. The exact speed depended on the complex details of how the gas flowed onto the growing planet and how the planet's gravity interacted with the surrounding disk. The spin rates were also affected by large impacts during the final stages of planet formation. When planet-sized objects collided, they didn't just add their masses together, they also exchanged angular momentum. The angle and speed of impact determined whether the collision would speed up the planet's rotation, slow it down, or even change its axis of rotation. Uranus's extreme tilt almost certainly resulted from one or more giant impacts that occurred late in its formation. Inside these spinning giants, the story continues. The rapid rotation creates strong Coriolis effects that organize the atmospheric flows into bands and zones. Rising warm gas gets deflected by the planet's rotation, creating the jet streams that race around the planets at different latitudes. In Jupiter's case, these jets are remarkably stable, maintaining the same patterns for centuries or longer. The rotation also affects the planet's magnetic fields, which are generated by the movement of electrically conducting fluids in their interiors, liquid metallic hydrogen in Jupiter and Saturn, and perhaps ionic water solutions in Uranus and Neptune. The differential rotation, the fact that different parts of these planets spin at different rates, creates zones of shearing where adjacent layers of fluid slide past each other. These shear zones can become unstable, spawning turbulence and storms. The Great Red Spot on Jupiter, a storm larger than Earth that has persisted for centuries, exists in a region where different wind speeds interact. The storm itself rotates, but at a rate different from the planet's overall rotation, caught in a complex interaction between different atmospheric layers. As these planets continue their journeys around the Sun, their rotation rates change, though extremely slowly. Gravitational interactions with their moons cause tidal effects that gradually transfer angular momentum between the planet and its satellites. This process is the same one that has locked our moon so that it always shows the same face to Earth, though it operates much more slowly on the giant planets due to their enormous masses. Jupiter's large moons are very gradually moving away from the planet, carrying angular momentum with them, which means Jupiter's rotation is slowing down, but this process operates over timescales of billions of years. The interiors of these planets remain largely mysterious, hidden beneath thousands of miles of atmosphere and fluid layers. Scientists use the planet's rotation rates, combined with precise measurements of their gravitational and magnetic fields, to deduce what must be happening in the unseen depths. The exact rotation rate of the deep interior tells us about the distribution of mass within the planet and how rigidly different layers are coupled together. Variations in the gravity field, measured by spacecraft flying past, reveal how mass is distributed between the equator and the poles, which in turn reveals how the rotation has shaped the planet's interior structure. Each of these giant worlds continues to spin through the darkness of space, their days flashing by in fractions of an Earth day, their atmospheres swirling in patterns that have persisted for eons. The differences in their spin rates encode the history of the solar system's formation, the random chance of ancient collisions, and the ongoing physical processes that govern how fluids behave under extreme conditions of pressure, temperature, and rotation. Understanding why gas giants spin at different speeds means understanding not just these four worlds, but the principles that govern planetary formation and evolution throughout the universe, wherever giant planets circle other stars. Why some asteroids are made of metal? Most asteroids are dark, rocky bodies composed of silicate minerals similar to the rocks found on Earth's surface. But among the hundreds of thousands of asteroids orbiting in the main belt between Mars and Jupiter, a small population stands out as fundamentally different. These are the metallic asteroids, composed primarily of iron and nickel rather than rock. They gleam brightly in reflected sunlight, their surfaces shining with the luster of exposed metal. The most famous of these is Psyche, a massive asteroid about 226 kilometers in diameter that appears to be almost entirely metallic. Understanding why some asteroids are made of metal means understanding the violent history of the early solar system and the process by which planets form their layered structures of core, mantle, and crust. The story of metallic asteroids begins with planetary differentiation, the process by which a planetary body separates into layers based on density. When a planet or large asteroid forms, it starts as a mixture of materials, rock-forming elements like silicon, oxygen, magnesium, and calcium mixed with metallic elements like iron and nickel. If the body grows large enough and contains enough radioactive elements, it heats up from the decay of radioactive isotopes and from the energy of continued impacts as it accretes more material. When the temperature rises above the melting point of iron, about 1538 degrees Celsius, something dramatic happens. The iron, being denser than the surrounding silicate rock, begins to sink toward the center of the body. This process, called the iron catastrophe, releases enormous amounts of gravitational potential energy as the dense metal falls inward, further heating the body. The result is a differentiated structure with a dense iron-nickel core at the center, surrounded by a rocky mantle of lighter silicate minerals, and potentially a thin crust at the surface. This is the same basic structure that Earth possesses, an iron-nickel core containing about 32% of Earth's mass, surrounded by a silicate mantle and crust. Planetary differentiation occurred in the early solar system in bodies large enough to melt their interiors. Earth differentiated, Mars differentiated, Venus almost certainly differentiated. Even some large asteroids, like Vesta, which has a diameter of about 525 kilometers, underwent differentiation. Vesta has a basaltic crust formed from volcanic activity, indicating that it once had a molten interior with a metallic core. The asteroid Ceres, the largest object in the asteroid belt, at about 940 kilometers in diameter, shows evidence of differentiation as well. Once a body has differentiated into core, mantle, and crust, it becomes vulnerable to catastrophic disruption. The early solar system was a chaotic place, filled with planetesimals, asteroid-sized objects, colliding frequently as they orbited the young sun. Computer simulations of this period show that collisions were not just common, but inevitable. Some collisions led to accretion, with two bodies merging to form a larger one, but others were catastrophically disruptive, shattering one or both bodies into fragments. When a differentiated planetesimal is shattered by a sufficiently energetic collision, the fragments don't all have the same composition. Pieces from the core are metallic, pieces from the mantle are rocky, pieces from the crust might be volcanic basalts if the body had volcanism. These fragments become separate asteroids, each one representing a sample of a specific layer from the parent body. This is why we find three distinct types of asteroids in the main belt: C-type asteroids, which are carbonaceous and primitive, never having melted; S-type asteroids, which are stony and represent crustal and mantle material; and M-type asteroids, which are metallic and represent exposed cores. The M-type designation comes from their metallic composition, though determining composition from Earth requires spectroscopic analysis and radar observations. M-type asteroids are typically much more reflective than rocky asteroids. Their albedo, or reflectivity, ranges from about 10 to 18%, compared to 3 to 7% for dark carbonaceous asteroids. This high reflectivity occurs because metal reflects light efficiently compared to dark silicate minerals. The spectroscopic signatures of M-type asteroids show features consistent with iron and nickel, though definitively confirming their composition requires spacecraft missions or detailed radar studies. Radar observations provide particularly strong evidence for the metallic nature of M-type asteroids. Radio waves reflect differently from metal surfaces than from rocky surfaces. Metal is a much better radar reflector, and radar polarization measurements can distinguish metallic from rocky compositions. Studies using the Arecibo Observatory and Goldstone Solar System radar have confirmed that many M-type asteroids have radar properties consistent with metallic surfaces, supporting the interpretation that they're exposed planetary cores. The asteroid Psyche represents the most studied example of a metallic asteroid and the target of NASA's Psyche mission, launched in 2023 and scheduled to arrive at the asteroid in 2029. Psyche is unusual even among M-type asteroids because of its enormous size and apparently high metal content. If Psyche is indeed the exposed core of a differentiated planetesimal, it would be the only core of a planetary body that humans have ever been able to study directly. Earth's core lies 2,900 kilometers beneath the surface, completely inaccessible. Mars's core is similarly hidden, but Psyche's core is exposed, available for investigation. The composition of metallic asteroids reflects the composition of planetary cores more generally. Iron and nickel are the dominant elements, present in roughly the same proportions found in iron meteorites that fall to Earth, about 90% iron and 10% nickel, though with some variation. These proportions match what cosmochemical models predict for the cores of terrestrial planets. Additional elements found in smaller quantities include cobalt, phosphorus, sulfur, and carbon. Some models suggest that planetary cores might contain significant amounts of lighter elements, like silicon or oxygen, dissolved in the molten metal, but whether these would be retained in a fragmented, solidified core like Psyche remains uncertain. The value of metallic asteroids extends beyond scientific interest. These asteroids contain enormous quantities of valuable metals. A single metallic asteroid a kilometer across might contain more platinum group metals than have ever been mined on Earth. The asteroid 16 Psyche, if it's as metallic as estimates suggest, would contain iron alone worth quadrillions of dollars at current prices. Though of course, actually mining and returning such quantities would crash commodity markets and is far beyond current technological capabilities. Nevertheless, the concept of asteroid mining has captured imaginations and may become economically viable in the future as space access costs decrease and in-space manufacturing develops. Not all M-type asteroids are metallic, which complicates the picture. Some asteroids classified as M-type, based on their reflectivity and spectroscopic properties, might actually be enstatite chondrites, a rare type of rocky meteorites with high reflectivity, or other unusual rock types that mimic the appearance of metal. This demonstrates the difficulty of determining asteroid composition remotely. Only with spacecraft missions, sample return, or eventually human exploration can we definitively establish what these objects are made of. The formation of metallic asteroids also constrains the timing and locations of planet formation in the early solar system. Differentiation requires heating, which comes primarily from radioactive decay of short-lived isotopes like aluminum-26, which has a half-life of only 717,000 years. For aluminum-26 to provide significant heating, the planetesimal must form within a few million years of the solar system's birth, while aluminum-26 is still abundant. This timing constraint suggests that the parent bodies of metallic asteroids formed quickly within the first few million years of solar system history. The subsequent disruption of these differentiated bodies likely occurred during a period of intense bombardment, possibly associated with dynamical instabilities in the giant planet's orbits. The Nice model, named after the city in France where it was developed, proposes that Jupiter, Saturn, Uranus, and Neptune formed in a more compact configuration and later migrated to their current orbits. This migration scattered planetesimals throughout the solar system, dramatically increasing collision rates and leading to the disruption of many differentiated bodies. The timing of this instability, estimated at around 600 to 800 million years after the solar system formed, would have been late enough for the large planetesimals to have already cooled and solidified after their differentiation. Iron meteorites that fall to Earth are fragments of metallic asteroids, providing samples we can study in laboratories. These meteorites show distinctive crystalline structures called Widmanstätten patterns, interlocking crystals of two different iron-nickel alloys, camosite and taenite, that form only when molten metal cools extremely slowly over millions of years. The size and structure of these crystals reveal the cooling history of the parent body's core. Some iron meteorites cooled at rates of only a few degrees Celsius per million years, consistent with cooling in the interior of a body tens to hundreds of kilometers in diameter, exactly the size of the differentiated planetesimals that became the parent bodies of metallic asteroids. The Widmanstätten patterns become visible when iron meteorites are cut, polished and etched with acid. The two iron-nickel alloys etch at different rates, revealing the crystalline structure. These patterns are beautiful and distinctive, and they can only form under the pressure and temperature conditions found deep within planetary cores, providing strong evidence that iron meteorites, and by extension metallic asteroids, genuinely represent fragments of ancient planetary cores. The distribution of metallic asteroids in the asteroid belt provides additional clues about the formation and evolution of the solar system. M-type asteroids are found throughout the main belt, but are somewhat more common in the middle regions. This distribution might reflect where conditions were favourable for forming large, differentiated planetesimals and where subsequent collisions occurred that could disrupt them. The relative scarcity of metallic asteroids compared to rocky ones, M-types represent only about 5 to 10% of asteroids, makes sense given that a differentiated body's core contains much less volume than its mantle and crust combined. Some metallic asteroids might not be fragments of differentiated bodies at all, but could have formed through different processes. Certain types of impactors, if they struck at very high velocities, could strip away a body's mantle and crust while leaving the core relatively intact. Alternatively, some metal-rich asteroids might have formed from material that was already enriched in metals during the solar system's formation, though this seems less likely given what we know about how materials were distributed in the protoplanetary disk. The Psyche mission will answer many questions about metallic asteroids when it arrives at its target. The spacecraft will map Psyche's surface in detail, measure its gravity field to determine how mass is distributed internally, study its magnetic properties to search for evidence of an ancient magnetic field that might have existed when the core was still molten, and analyze its composition using spectrometers and cameras. These measurements will reveal whether Psyche is indeed a nearly pure metallic core, as many scientists suspect, or whether it has a more complex structure with rock mixed in or covering parts of the surface. Understanding metallic asteroids means understanding planetary cores, the process of differentiation, the violence of the early solar system, and the building blocks from which planets formed. Every metallic asteroid is a window into planetary interiors, exposing material that would otherwise remain forever hidden beneath thousands of kilometers of rock. These fragments of ancient cores, forged in the heat of differentiation and revealed by catastrophic collisions, represent some of the oldest processed materials in the solar system. Samples of the massive bodies that either grew into planets or were destroyed in the chaos of planetary formation, leaving behind their metallic hearts orbiting the sun as testament to the violent processes that shaped our cosmic neighborhood billions of years ago. Why stars explode when they die? For millions or billions of years, a star exists in a state of perfect balance. Gravity pulls inward, trying to compress the star, while the heat and pressure from nuclear fusion in the core push outward, resisting that compression. This equilibrium, this careful balance between opposing forces, allows stars to shine steadily for incomprehensible stretches of time. But eventually, inevitably, the fuel runs out. For some stars, death comes quietly, a gentle fading as they shed their outer layers and cool into obscurity. But for the most massive stars, death is anything but peaceful. When these giants exhaust their nuclear fuel, they don't fade. They explode with such violence that a single dying star can briefly outshine an entire galaxy of hundreds of billions of stars. The path to a supernova explosion begins with the structure of massive stars and how they generate energy. Stars like our Sun fuse hydrogen into helium in their cores, a process that releases energy and provides the outward pressure needed to support the star against its own gravity. But massive stars, those with at least 8 times the Sun's mass, don't stop at hydrogen fusion. When the hydrogen in the core is exhausted, the core contracts and heats up until it reaches temperatures high enough to fuse helium into carbon and oxygen. This is just the beginning. For massive stars, nuclear fusion proceeds through multiple stages, each burning a different fuel. After helium burning comes carbon burning, then neon burning, then oxygen burning, and finally silicon burning. Each stage produces heavier elements as its ash, and those ashes become the fuel for the next stage. Each stage also burns faster than the previous one because it occurs at higher temperatures and releases less energy per fusion reaction. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, but only days fusing silicon. The star develops a layered structure, like an onion, with each shell fusing a different element. The outermost layers still contain mostly hydrogen. Deeper in, a shell fuses helium. Deeper still, shells fuse carbon, neon, oxygen, and silicon in succession. At the very center lies an iron core, about 1.5 times the mass of the Sun, but compressed into a sphere roughly the size of Earth. This iron core is the end of the line. Iron occupies a special place in nuclear physics. Elements lighter than iron release energy when fused together. This is what powers stars. Elements heavier than iron release energy when split apart through fission, but iron sits at the peak of the binding energy curve. Fusing iron nuclei together doesn't release energy, it requires energy. The iron core cannot generate heat through fusion. It's an inert ball of matter, supported only by electron degeneracy pressure, the quantum mechanical resistance of electrons being compressed too closely together. The iron core grows as the silicon-burning shell above it continues converting silicon into iron. Each second, tons of iron are added to the core. The core is already incredibly dense, about 10 billion kilograms per cubic meter, and as it grows more massive, it also grows hotter and denser. The electrons supporting the core are squeezed into higher and higher energy states, reaching energies where they can do something remarkable. They can merge with protons. This process, called electron capture or inverse beta decay, occurs when an electron is forced into a proton, creating a neutron and releasing a neutrino. The neutrino immediately escapes from the star at the speed of light, carrying energy away. This removes electrons from the core, reducing the electron degeneracy pressure that's supporting it. The core contracts further, squeezing more electrons into protons, creating more neutrons, removing more pressure support, causing further contraction. This runaway process accelerates catastrophically. Subrahmanyan Chandrasekhar calculated in the 1930s that electron degeneracy pressure can support a maximum mass of about 1.4 solar masses, now called the Chandrasekhar limit. When the iron core exceeds this limit, electron degeneracy pressure can no longer hold it up. The core collapses. What happens next occurs in less than a second, but releases more energy than the star produced during its entire multi-million-year lifetime. The core implodes at velocities reaching 70,000 kilometers per second, nearly 1/4 the speed of light. The outer part of the core falls onto the inner part, compressing it to densities exceeding that of atomic nuclei. At these densities, around 400 trillion grams per cubic centimeter, nuclear forces become repulsive rather than attractive. The collapse halts suddenly, like a ball hitting a concrete floor. The abrupt halt of the inner core creates a shock wave that propagates outward through the infalling material. This bounce shock wave contains enough energy to blow apart the entire star, but calculations show that it stalls within milliseconds, unable to push through the still infalling outer layers. For decades, this posed a major theoretical problem. How do stars actually explode if the bounce shock stalls? The answer lies in neutrinos. During the collapse, protons and electrons combine to form neutrons, releasing vast numbers of neutrinos. The newborn neutron star at the core, incredibly hot, temperatures exceeding 100 billion degrees, produces additional neutrinos through various processes. In normal circumstances, neutrinos barely interact with matter. Trillions pass through your body every second from the sun without causing any effect. But the matter in a collapsing stellar core is so dense that even neutrinos can't escape immediately. They diffuse outward over several seconds, and during this time, a tiny fraction, less than 1% of them, interact with the infalling material. This sounds negligible, but the total neutrino energy is staggering, about 10 to the 53 ergs, roughly 100 times the energy the sun will radiate during its entire 10 billion year lifetime, released in just 10 seconds. Even if only 1% of this energy couples to the stellar material, it's more than enough to revive the stalled shockwave and drive the explosion. The outer layers of the star are blasted into space at speeds of 30,000 kilometers per second or more. This core collapse supernova, designated Type 2 if hydrogen is present in the spectrum, or Type 1b or IC if the star lost its hydrogen envelope before exploding, is the fate of all massive stars. The explosion is so energetic that it creates elements heavier than iron through rapid neutron capture. During the few seconds of the explosion, neutrons are so abundant that nuclei can capture many neutrons in quick succession, building up elements like gold, platinum, and uranium that cannot be created through normal stellar fusion. Every atom of gold in existence was created in supernova explosions or in the mergers of neutron stars. The only direct detection of supernova neutrinos occurred on February 23, 1987, when neutrino detectors on Earth registered a burst of neutrinos from supernova 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The neutrinos arrived about 3 hours before the light became visible, exactly as predicted. The neutrinos escaped during the core collapse, while the light had to wait for the shockwave to reach the star's surface. This detection confirmed the core collapse mechanism and marked the beginning of neutrino astronomy. There's another type of supernova with a completely different mechanism, the Type 1a supernova. These occur in binary star systems where a white dwarf, the dense remnant of a sun-like star, accretes matter from a companion star. As the white dwarf gains mass, it approaches the Chandrasekhar limit. When it crosses this threshold, carbon fusion ignites throughout the entire white dwarf, almost simultaneously, not gradually, from the center outward. The fusion releases so much energy that the white dwarf is completely disrupted. There's no neutron star remnants left behind. The entire star is blown apart. Type Ia supernovae are remarkably uniform in their energy output because they always occur at approximately the same mass, the Chandrasekhar limit. This uniformity makes them valuable as standard candles for measuring cosmic distances. Observations of distant Type Ia supernova by Saul Perlmutter, Brian Schmidt, Adam Ress, and their teams in the 1990s revealed that the universe's expansion is accelerating, leading to the discovery of dark energy and earning the observers the 2011 Nobel Prize in Physics. The energy released in a supernova is distributed across different forms. About 99% goes into neutrinos, which escape into space carrying information about the core collapse. About 1% goes into kinetic energy of the ejected material, the blast wave that expands into space. Only about 0.01% goes into light, but this is still enough to make the supernova visible across billions of light years. For a few weeks, a single supernova can outshine its entire host galaxy. The remnant left behind after a core collapse supernova depends on the core's final mass. If the core is between about 1.4 and 3 solar masses, electron degeneracy pressure fails, but neutron degeneracy pressure succeeds in halting the collapse, creating a neutron star. If the core exceeds roughly 3 solar masses, even neutron degeneracy pressure cannot stop the collapse, and the core continues collapsing into a black hole. The exact threshold remains uncertain because it depends on the equation of state of nuclear matter at extreme densities, which is not precisely known. Supernova explosions enrich the interstellar medium with heavy elements. The carbon, oxygen, silicon, and iron in the ejected material mix into interstellar gas clouds, raising their metallicity, the abundance of elements heavier than hydrogen and helium. These enriched clouds eventually collapse to form new generations of stars and planets. The Sun and Earth formed from material enriched by previous supernova. Every element heavier than lithium in your body was created in a star and dispersed by a supernova or stellar wind. The shockwave from a supernova can trigger new star formation by compressing nearby molecular clouds. The expanding remnant, a shell of hot gas and energetic particles, can remain visible for thousands of years. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova that occurred in 1054 AD and was recorded by Chinese astronomers. At its center sits a rapidly spinning neutron star, a pulsar rotating 30 times per second, powered by the rotational energy it inherited from the collapsed core. Supernova rates in galaxies depend on the star formation rate and the mass distribution of stars being formed. The Milky Way experiences roughly 2 to 3 supernovae per century on average, though we haven't witnessed a nearby visible supernova since Kepler's supernova in 1604. Most occur hidden behind dust in the galactic plane, their light obscured but their effects, shockwaves, cosmic rays, heavy element enrichment, rippling through the galaxy. The most massive stars can experience even more exotic deaths, stars exceeding roughly 130 solar masses might become pair instability supernovae, where gamma rays in the core become so energetic that they spontaneously convert into electron-positron pairs. This removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is destroyed. No remnant of any kind survives. Stars more massive still might collapse directly into black holes without exploding at all, with all their mass disappearing behind an event horizon in silence. Understanding why stars explode when they die connects nuclear physics, quantum mechanics, general relativity, and hydrodynamics. It explains the origin of elements, the formation of neutron stars and black holes, the enrichment of galaxies with heavy elements, and the triggering of new star formation. The death of massive stars through supernova explosions is not just destruction, it's creation, recycling stellar material back into space, enriched with new elements, ready to form new stars, new planets, and perhaps new life, continuing the cosmic cycle that has built the complex, element-rich universe we inhabit today, all initiated by the catastrophic collapse that occurs when fusion finally fails and gravity wins its ultimate victory over the force that gave the star life.